Hey, okay. It's time for Cat Theory 2. Did I rename it right? Okay, I did. That's good. So, we left off somewhere here last time, and now there's just some exercises to do before we move on to the next part. So let's just do, some of them, right? Oh, we didn't do exercise number 1. Alright, so we left off here, I think. Alright, so there's this stuff over here, which we haven't read yet. One very useful sort of set is a singleton set, a set with exactly one element. Fix one of these, say me, and call this set 1. Look at what the maps from 1 to John, Mary, Sam are. There are exactly 3 of them, right? So there are only 3 possible ways that you can create a map between this set that contains 1 object and a set that contains 3 objects. Right? So a point of a set X is a map from 1 into X, because that map, sort of points only to a singular object in that set, right? So this map is what you can think of it as, like, isomorphic to the point John over here, and this map here that points to Mary represents sort of Mary itself. Right? If A is some familiar set, a map from A to X is called an A element of X, thus 1 elements are points. Okay, since a point is a map, we can compose it with another map and get a point again. Right? So this thing points to John, and John points to egg. So if we compose it, the whole thing just points to eggs. So it's just this, right? And what is this? This is a map from 1, right? 1 to X. So this is also a point. And well, it clearly just points to eggs, because just following from here and here, right? This is a map from 1 to some set X. So it's this composition F composed with John is the point eggs. To help familiarize yourself with the category of finite sets, here are some exercises. Well, let's see exercise 1 first. It's just filling in the diagrams, but I think this should be easy, right? For example, H composed with G, so this thing goes here, and then this thing goes here, so we know that HG, this point goes here. So we're just following this, and then this up here. This thing just goes here, this thing goes here, straight here, and up here. So this point goes here, this point also goes here, and so on. You can just fill in the blanks. I think this is just, we already know how to do this, so let's just skip through it. I'm sure it's logical how we can do that. How many different maps are there with domain A and codomain B? One example is this guy right here. So A is John, Mary, Sam, B is X coffee. So I think there's a formula. Of course there's a formula, but I forgot what it is. So if you have 3 things here and 2 things, how can you how do you choose the options here? So we can shift this into like a combinatorics problem with like the C and the P, like the stuff that we learn in high school. I just need to figure out how we can framework this problem into that case. it's not like arranging three things in two different places, because like this is a map, even though everything just gets mapped onto this single thing over here. Oh, it's like, let's say this is 1 and this is 2. So it's like 1, 1, 1 represents everything being mapped to 1. There's like 1, 2, 2, 2, 2, 2, and so on and so forth. Right? So it's like three spots, and then like, how can we like fill in this thing over here? Well, there's like, wait, how do we do this again? Well, there's two choices over here, right? We can put in either 1 or 2 choices. And then there's two choices here, you can put in either 1 or 2. And then there's two choices here, you can put in either 1 or 2. So it should be 8 question mark. How about duplicates though? Wait, do duplicates count? Like 2, 2. Wait. So yeah, right? So it's like, hold on. So there's three things over here. And we can separate these into like, this is 1, this is 2. And we can separate these down again into like 1, 2, wait, 1, 1, blank. This is 1, 2, blank. This is 2, 1, blank, and then 2, 2, blank, and then these have two further options again. Right? Blah, 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 blah. So it's 1, 2, 3, 4, 5, 6, 7, 8. Yeah, the formula does work. And like, this sequence of three things corresponds to the function. Right? So let's say we pick this guy over here. This will be 1, 1, 2. This represents the function. It sends the first object to the first point, the second object to the first point, and then the third object to the second point. So the sequence 1, 1, 2 is represents this function 1, 1, and 2. Right? So since the sequences represent the function, then when we're counting these sequences, we're just counting the functions. We're just frameworking the problem in a much easier way. So 8 is the answer, and I think it's just how many points here to the power of how many points here. So if we have 4, for example, then that would be 2 to the power of 4, and so on. So we can generalize this problem easily and solve other similar problems as well with that formula. I'm pretty sure that's how it works. So let's see exercise 3, same but for maps A into A, B into A, B into B. Well, we know how to do it already, right? So let's just skip through all of these because we already have like, a general formula for that. Right, how many maps? Let's just do B because B has 2 points and that'll be easier. How many maps that go from B into B satisfy, G circ G equals G, or G composed with G equals G. So we have B, which consists of 2 points. The name of these 2 points don't really matter. All we need is Okay. So this is 0.1, 0.2, 0.1, 0.2. And how many maps are there? Well, there's 1, 1, 1, 2, 2, 1, and 2, 2. Those are the maps. And now we need to check each of these maps to see if G composed with G is equal to G again. So 1 goes to 1 and the second point goes to 1, right? So if we compose it again, hold on, that means we need to do this again, 1, 2, and we have this guy right here and this guy right here. Alright, if we compose these two maps together, what we obtain is 1 goes to, we follow the arrow, 1. 2 goes to, we follow the arrow, 1. This is the map G, this is the map G. So if we take G circ G, we get this point goes to here, and this point follow the line goes to here as well. So G circ G is the same thing as G, because if you look, G goes from here and here, G circ G also goes from here and here. So G is equal to G circ G. Right, so we can put a check mark there. And by the same logic, then 2, 2, which is this guy, right, should also count as well. I wonder if there's like a quick way to check it instead of doing it manually, some clever logic trick that we can use. So 1, 2 goes here, and then we repeat that again. Wait, no, that's not 1, 2. 1, 2. Oh, 1, 2 is just like this, right? And we have 1, 2 again, which just goes like this. Right, the first object gets mapped to the first point. First object is mapped to the first point, second object maps to the second point. Yeah, so this also does count, because clearly, you know. And we have 2, 1. So that's just the first object maps to the second point. Second object gets mapped to the first point. And we repeat that again. So this goes here, this goes here. So just check as well. So all of them. Turns out all of them. Interesting. Maybe the answer is different for the set A with 3 objects, but you can check that out for yourself. I'm not gonna bother. Let's do either one of exercise 8 or 9. Let's do the easier one. Right, BAB. Whew. Okay. Right. So B is 2 points, A is 3 points, B is 2 points again. And then we need the composition to equal the identity. Right, so there's, you know, this, and, well, it needs to be a function, so there needs to be an arrow from here to here. Well, it doesn't matter. It can be either here or it can be either here. It doesn't really matter, right? Because the composition will not sort of give a shit about like this point in the middle over here, right? But this point needs a mapping because, well, that's just the definition of a function. Everything in the domain needs to map into something, right? But if you take the composition, this is H, this is K, that really won't get taken into account. Because if you map H and K, you follow the arrow from H to K, H, K, hk. So notice that wherever these arrows point to, right, can point to here, doesn't sort of have any effect towards, how we determine where h and how we determine how the composition is formed, basically. So these are two options already. And then there is, well, the same thing again, but we can have crisscross, and then this goes down, this goes up, right? If you follow the path. So these are another two options, right? Because we have this version where we have this pointing down here, and then we have another version where this middle point points up here. And we can also have no, I think that's it. I think that is it. That should be it. Because the only other option to consider is if these two things map into like the same point over here. Or I guess it can map into the middle as well. Like for example, we can have this map into the middle, and then this will go here. Wait, hold on, then this will go here. Wait. Oh god, I'm confusing myself here. This goes here, this goes here, this goes here. And then of course this can also go here if it wants to. Right, so that's another option, so that's another two. So I guess there's a lot. There's a whole lot. Right, because then you can also move this arrow up here. Just imagine like moving this into this position, and then this arrow here also gets transferred over here like that. Yeah, there are many different possibilities, and you can manually check them, but I won't because I feel like that's a waste of time. Point is, like, we know what's going on. So these are some of the things we've covered. Yep. Right, so let's go into the second session then. Review of Article 1. Right, so that's just stuff that we know already. That is a fairly accurate description of what a map is. Well, let me take a drink. Mm-hmm. Right, so a function is basically just a domain and then a codomain and instructions for how to convert the elements of the domain into the elements of the codomain. So here the domain and codomain is numbers, so we need to give an instruction of how to convert one number into another number, and this is one of the instructions, add 1 and then square. But then over here, this is like one instruction, this is another instruction, square the input, double the input, add the two results. So f of x, you square the input, you double the input, you add the two results, and then add 1. So notice that this is just x plus 1 squared by, basic algebra stuff. So we can give them two instructions, but ultimately they're equivalent to one another, right? They map to the same points, right? If you put 1 as x, then this gives a number, this also gives a number, and they are going to be the same number. So the point 1 is mapped to the same point. So f of 1 is 3, no 4. I'm so dumb. Using this instruction, and over here using this instruction, it's also 4 as well. So you can see that in the picture over here. And so even if the instruction is different, the functions are still the same because, well, ultimately they map the points to the same points. Yeah, as long as they produce the same result, then they are the same map. That the two rules are the same rule, which they obviously are not. In particular, one of them takes more steps than the other. The idea is that the function or map of sets is not the rule itself, but what the rule accomplishes. Yep, okay. The idea is that the function or map of set is not the rule itself, but what it accomplishes. Yep, makes sense. This aspect is nicely captured by the pictures or internal diagrams. In categories other than the category of sets, a map from A to B is typically some sort of process for getting from A to B, so that in any category, maps F and G are not considered the same unless they have at least the properties. 1, F and G have the same domain, F and G have the same codomain. Of course, there may be many different maps from A to B, so that these two properties alone do not guarantee that F and G are the same map. If we recall that the point of a set A is a map from a singleton set 1 to A, we see that there is a simple test for equality of maps of sets A to B, which is given by F, and A to B, which is given by G. If for each point 1 AA, F A equals GA, then F equals G. So oh, they're not the same because this is Emilio, this is Sherry, so this set is different than from this set. So the codomain of the sets are different, so that's why it's not. This thing over here, I don't know, it just feels like it's obvious, or like doesn't introduce anything new. Obviously, if you have a set which consists of a single point, and then you have A and B, and then you have first, say, if for each point, right? So we check a point, and then we have, different maps, F and F and G, yep. And if F composed with 1 and G composed with 1, turn out to be the same, so these turn out to be the same points, then f and g, are actually the same function, right? But then you're testing, sort of maps between sets, right, to see whether they're equal. But then to test whether these two functions are equal, you need to test whether these two functions are equal, which is well, I guess, I don't know, maybe what they're trying to say is that these are not functions anymore, because these are now points, and you can obviously test equality between points. So these are no longer functions, these are points. So it reduces testing the equality of functions into equality between points. I remember from, I don't know, back here. Where was it? Yeah, since a point is a map, we can compose it with another map and get a point again. So we compose a point with a map, we get another point again. Same over here. So this is a point, this is a point. And yeah, I thought it was contradictory because I thought this was a mapping at first. And it's like, to test whether two maps are equal, you have to check whether these two maps are equal. And this is like a circular argument sort of thing. But if we consider them as points and not as mappings, then it could work. So there's no contradiction there. So these are the same even though the pictures are not the same. It's just where the arrow lands is the problem, is the determining feature. And I think this is just basic stuff. It's just explaining the notation, which I'm sure everyone is already familiar with. Is this correct? Hold on, let's check before we see. Let's see. Did you do this right, Chad? So these three go here, and then we can write here, right? I think, hold on. Yeah. Let's do this. Right. So these go here, 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 and this goes down, up. So here, this goes here, here, which goes here. This goes here, here, which goes here. This goes here, here, which goes here. So did you do this right, Chad? No, you didn't, you idiot. You forgot this line over here. Yeah, if you forgot this line over here, one of the points of the domain HG has been left without an assigned output. What an idiot, Chad. How could you make this mistake? This deficiency won't matter for the next step because that information is going to get lost anyhow. But it belongs in this step, and it is incorrect to omit it. Chad's trouble was that in drawing HG, Chad's trouble was that in drawing HG, he noticed that the last arrow would be irrelevant to the composite HGF, so he left it out. Also, that's what we sort of did earlier. If we just Control Z, where was it? Oh yeah, like these things here, right? Even though when we take the composition, this middle point here does not matter, we still need to include it anyway, right? Even though like it doesn't matter in the grand scheme of things if you take the composition, it's still important to include like where this thing gets mapped into, which is what I say. So like here, even though it's irrelevant, yeah, it's still important. So that's just repeating the concept that I gave earlier. Seems the principle is like in multiplication, where the order in which you do things doesn't matter, you get the same answer. So HG composed together, composed with F is the same as GF composed with each other, and then you compose that with F. Like, if you put brackets here and you put brackets here, doesn't matter. Does it? The order does matter. Oh yeah, within two things, within two. Oh, oh no, he didn't meant. Oh, he didn't mean like this order, like the order in which you do things or bracket things. He meant like the actual order, like flipping G and F around or H and G around, like the actual position instead of like the bracket thing. So if you flip the positions around, like H and G together, obviously it'll make things different. So this is FG. If you compose them together, you get this thing here. I guess it wants us to fill it out, right? For ourselves, which let's do just for illustrative purposes. Mike goes to Mike, then goes to Mike. So here, so what that would look like. Sherry goes to Fatima, goes to Sherry. So Sherry goes to Sherry, Fatima goes to Sherry, goes to Mike, so Fatima goes to Mike. Right. So this is GF. So now this one will be FG. Right, what is F? F is, we'll use like 112, right? 112. 1, 1, 2. And G is 1, 3, 2. 1, 3, 2. 1, 3, 2. Now if we do composition, Mike goes to Mike, goes to Mike. Sherry goes to Mike, goes to Mike. Fatima goes to Sherry, goes to Fatima. And obviously this is different from this. Okay, cool. The two results are different. in composition of maps, the order matters. When I was little, I had a large family, and in large families, there are always many small chores to do. So my mother would say to one of us, wouldn't you like to wash the dishes? But as we grew, two or more tasks were merged into one. So that my mother would say, wouldn't you like to wash and then rinse the dishes? Or scrape and wash and then rinse and dry the dishes, and you can't change the order. Yeah, it makes sense. You'll make a mess if you try to dry before scraping. The associative law for a task says that the two tasks, scrape then wash, then rinse then dry, and scrape then wash, then rinse, then dry, accomplish the same thing. I mean, yeah, 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 because the brackets, like, yeah, yeah. Yeah, the parentheses or the grouping between them does not matter. Mm-hmm. Right, so these two arrows here and here disappear. Right, you just take this guy and then going down here, this guy, and then going down here, which is, just these two map to the same point, this point maps to here, so these two map to this point. And then you lose a bunch of information, in particular this arrow and this arrow has nothing to do with what the composition is over here. So from here you can construct the composition, but from the composition you cannot deconstruct this into this because the composition over here does not have the information of this guy and this guy. So some information is lost there. To understand this, you should realize that the composite of two maps is supposed to be another map so that it just has a domain, a codomain, and a rule. The pasting together of two diagrams is not the composite map, it is just a rule to find the composite map, which can be done easily by following the arrows to draw the diagram of the resulting composite map. The point of erasing all the irrelevant detail like the extra arrows is that the simplified picture really gives a different rule which defines the same map but a simpler rule. Okay. Suppose you carry a sleeping baby on a brief walk around town, first walking in the hot sun, then through the cool shade in the park, then out in the sun again. What? Okay. Let's try to understand this. The map W assigns to each instant your location at that time, and the map T assigns to each spot in Buffalo the temperature there. Temperature line has at its points physical temperatures rather than numbers which measure temperature on some scale. A baby is affected by temperatures before learning of either Fahrenheit or Celsius. The baby was hot, then cool, then hot again, but doesn't know the two maps were composed to get this one map. Like my issue with this example is, okay, so like they say if you compose these two things together, then you'll know how the baby is feeling at like that point in time. So if you have, time and then temperature and then, oh no, like location and then temperature, obviously you can compose these two maps together. How would that look like? Hold on. Yeah, like this. Um, then you'll get how the baby is feeling at the time. So like, um, at second or like hour one, you were at like this, the park, right? So how do you figure that out? You map the hour one, right? You're converting time into location. So the hour one gets converted with F to a park. And the park G was hot at the time. So hour one, you were at the park with the baby and it was hot at the park. So if you compose these two together, you get that the baby was hot at the first hour mark. Like my main issue is this map over here from park to hot. It's not always constant because it always, depends on the time of the day, right? What if it's nighttime? Then obviously the park will be cool. So the park can either be cool or hot depending on, the time as well. So this map is sort of dependent on time as well as a factor here. So it's actually more complicated than it actually seems. Obviously, I think the example purposely ignored this minor detail, but it could, throw some people off because they could be looking for, these details when it's not actually there. So they should have picked a better example, I think. Right? And you can like think of these as like sets as well. Like T is the set of all like time. Like you have hour one and a half, hour two, hour three, hour four, and so on. Like all throughout the day, location, obviously you can think of that as a set as well. Like park, library, blah 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 blah. And Celsius, like it's just, or even simpler, you can just say hot or cold. And then this is just 2 points. And then a location can either be hot or cold, right? So at time 1 you were here, at time 2 you were here, at time 3 you were here. And then if you want to figure out like how the baby is feeling at a certain point in time, you just have to follow the arrows around, i.e. just compose the two maps together. So that's probably what it meant, but like I said, there are some issues which I mentioned. An example of different rules for a map. The measurement of temperature provides a nice example of different rules for a numerical map. If one looks at a thermometer which has both scales, Celsius and Fahrenheit, it becomes obvious that there is a map. Numbers change from Fahrenheit to Celsius numbers. Okay. Which sends measure in degrees Fahrenheit of a temperature to the measure in degrees Celsius of the same temperature. In other words, it is the map that fits in the diagram. This guy. Mm. You have a temperature. You can either represented in terms of Fahrenheit or degrees Celsius, obviously that representation will be in the form of a number. And obviously you can also convert between these two numbers together. How is this map calculated? Well, there are several possible rules. One of them is subtract 32, then multiply 5/9. Another is add 14, multiply by 5/9, then subtract 40. Notice that each of these rules is itself a composite of maps so that we can draw the following diagram. So to change from Fahrenheit to Celsius, we can just go through this path instead, which is more explicit. Or we can go through this path. Right, so like, let's say this is F and G, this is, I don't know, A, B, and C, so F, or like G composed with F. Is it F composed with G or G composed with F? And then, but you know what I mean. This composed with this is the same as these three composed together. Alright, yeah, makes sense. And we can verify this. This is actually interesting. So like, if you have a number, x, subtracted with 32, and then multiplied by 5/9, is the same thing as x plus 40 times 5/9 minus 40. This is true? Well, that's interesting. We can just add 40 on both sides. X minus 32, 5/9 plus 40 is equal to x plus 40, 5/9. Cancel, cancel. This times 9/5. 5/1/8. 8 times 9 is 72. And 72 plus -32, let me guess, is just gonna be 40. Which, yeah, it is. So yeah, that's why it works out. That was interesting. Okay. External diagrams. When does this end? Because I need to go sleep. Session 3, we're close, we're close. The pasting of the diagrams to calculate composition of maps is nice because from it you can read what F does and what G does, and also what the composite G of F does. This is much more information than is contained in G of F alone. In fact, internal diagrams aren't always shown. We use schematic diagrams like those in our temperature example, or this. These are called external diagrams because they don't show what's going on inside. In session 1, we met an external diagram when discussing Galileo's ideas. Yep. Problems on the number of maps from one set to another. Let's work out a few problems that are not in Article 1. How many maps are there from set A to the set B in the following example? Wait, what formula did we come up with again? Jesus. What was it? We had 3 and then 2. And I remembered that the answer was 8. So that came from 2 to the power of 3. So this side to the power of this side. But that doesn't work out because if we do this thing, for example, we'll get 1 to the power of 4, which is 1. And, well, obviously it's not 1, there are... Oh, it is 1. It is correct. That just felt like a bit counterintuitive. There is only one map, right? How do you do a mapping? Well, a function from A to B needs to map the points of A to the points of B. And every point in the domain, this is the domain, this is the codomain. Every point in the domain needs to have a mapping. So you need to have a mapping. The only possible mapping is here. So there's only a single point. The only possible mapping is here. The only possible mapping is here. The only possible mapping is here. And there's no other set of combinations that you can make. So there is only one mapping, no matter how many. This is 4. If you add 5, then there's only one mapping from 5 objects into 1. There's only one mapping from 6 objects into 1, and so on and so forth. Yeah, exactly one map. All elements of A go to Emilio. This one is there 4 maps, because it's 4 to the power of 1 instead of 1 to the power of 4. The set of all purple people eaters in this room. And of course there's no purple people eaters. So this set will be empty. Right? And this diagram doesn't have any arrows, but it doesn't need any. So basically it's 0 and 4. Right? So it's... Wait, what was it again? So it's left side to the power of... Wait. Right side to the power of left side. Yeah, right side to the power of left side. So if you have 0, 4, then it's right side to the power of left side, which is 1. Wait, anything to the power of 0 is 1, right? Yeah. So the formula doesn't work if you like extend it to 0, extend it to include 0. Which, you know, is unfortunate, but they... Oh, it is correct. 1, 1. Oh god, I was confused. Jesus, okay. So it does still work. There is one map, but there is no map. Okay, like, if you have 0 objects, then obviously you can't draw an arrow from here to here because it doesn't have, like, a source. But even though there is no mapping, it is still a map. Because, well, I don't know, it's a bit hard to explain, but I sort of get their idea here. Yeah, without giving yourself a headache. That is a tall order. So, like, a function is, like, it consists of a domain and a codomain. We have those, right? Because the empty set, even though it contains nothing, it is still a set. An empty set is still a set. And a set can be a domain, or a domain rather can be a set, or is a set. So the empty set does work as a domain. This 4 object set, of course, works as a codomain. It's a 4 object set. So we have a domain and codomain. And then what is the other ingredient for a function? it is instructions for taking objects from the domain and converting them into objects in the codomain. But since there are no objects in the domain, we don't need any instructions. The instructions are unnecessary, so that sort of requirement is automatically fulfilled, right? It's like someone asks you to, like, hey, if there's a box in that room, bring it here. So you go into the room and there's no box, and then it's like, let's say your officer or like your boss or whatever says, like, well, yeah, if there's a box in that room, bring it here. And then you go to the room and there's no box in the room, right? So you go back and say, well, there's no box in the room. And then your supervisor, your boss says, well, okay, then I guess your job is done because that was my only task for you for today. And yeah, even though you did nothing, the task is still completed. You get what I mean? Even though, yeah. Yeah, that's sort of the idea or principle behind it. I hope I gave like good enough analogy. But I think that's the sort of thing that they're trying to communicate. It's like the condition is automatically fulfilled if you have like no objects and nothing to work on. Now we reverse the previous example, that is, now we have 4 and 0, left side to the power of right side is 0, so it is indeed 0. So what is the reasoning here? Well, it's okay for this guy to not have an arrow, right? Because an arrow needs to have a source, and then the source needs to go somewhere. But since we have no source, we don't have anything to work on, so it's like, our job is done. We need to draw arrows from points to points, but we don't have any points to begin with, so our job is done, right? But over here we have points, right? It's like our boss says, take these boxes somewhere. So you go into the room and there are 4 boxes, and you take them, but you're sort of lost as to like what to do with the boxes. So the boxes are there, and you have to do something with them, but you can't because, well, there's nothing to, transfer the boxes to. Whereas over here, you have, just think of it as like these are boxes, and then you have to transport them somewhere. Like this is a location, and then like your boss is giving instructions on like move the boxes here and here and here and so on and so forth. So you go into the room, there are 4 boxes, and well, you can't really do anything because like you pick the boxes up, like where do you move it to? The set of locations is empty, right? There's just no options for where to move the box to. Whereas over here, you go into the room, there are no boxes, so you're like, well, I don't have a job here to do. So okay, that's like, yep. But over here is a no-go, because you actually have a job to do. There is a job to do. There is a task that you can't really execute. So there is no, mapping. Right? Each of them is impossible. I think that's what it means. That's why there is no mapping here, but over here it is indeed a valid mapping. Right? Because it is an instruction, and you successfully completed the instruction. Like, because there's no boxes there, the instruction is automatically completed. Your boss says, move move the boxes to, certain location, blah blah blah. You go into the room, there are no boxes, so your job is done. Right, the task is complete. Right, you can go back to your boss and say the job is done. And he won't blame you for that, because your boss said, well, move the boxes, but if there are no boxes, then yeah. And the next example they gave is where both sets are empty, and it's again the same thing. You go into the room, this box's location. Even though you have no location, well, it's like the job is complete in the first place. Like, there are no boxes, so the fact that there are no locations is not an issue, because you don't need to worry about where to move the boxes. Right, if you had to move a box, then this would be a problem because you don't know where to put it. But if you have no boxes in the first place, then there is none of that problem to deal with. Right? If you had a box, then the fact that you have no location is worrisome. But if you don't have the role or the job of moving the boxes around simply because of the absence of boxes, then the fact that there is no location to put the boxes is not an issue in the first place. So again, like, your task is complete. It's not an issue that there's no location available. So that's why this is considered a mapping. Right? The mapping is, well, the job is automatically complete no matter what. That's what the mapping means. Obviously, like, if you have a normal example with the box and location analogy I just came up with, then your boss tells you to move boxes into a certain location, then, well, yeah, there is like one job that you can do, that is move box 1 into this location, move box 2 into this location, because that's the only combination there. Whereas if you have something like this, then there are 4 ways to do the job. You can move these 2 boxes into this location, or you can move these 2 boxes into the second location, or you can move box 1 into location 2, box 2 in location 1, box 1 in location 1, and box 2 in location 2. So the 4 options there is just 2 to the power of 2, 4. This is just 1 to the power of 2, 1. So there's only one way you can do the job here. There's 4 ways you can do the job here. There's only one way you can do the job here, and that is just go into the room. Notice that like there is nothing to do here, and go report back to your boss. And, well, your boss will still have to admit that the job is done, because, well, the job is, well, empty in the first place. There is nothing to do. But you can still report that the task is still accomplished, because your boss said move the boxes. Well, there are no boxes to move, so that's just automatically done. Same case over here. You can report to your boss that your job is complete, and, well, that's like only one thing, right? That's the only option that can happen. That's the only possibility that can happen, in contrast to when you actually have boxes and actually have locations. Then you have different choices. You have 4 choices on how you want to move the boxes to the location. And at this example over here, you have 4 boxes. You go into the room, you have 4 boxes, and then you have no locations. So you can't report to your boss and say the job is done, because your boss told you to move the boxes, and there are boxes, but it's impossible to move them anywhere because you have no location to work with. So that's that. And we are at session 3, almost 50 pages out of 400. That is 1/8 of the way there. Not bad. Well, I mean, I guess like you can't really count the first part, which is like the just the introduction and stuff. But yeah, we're covering a lot of ground in a short amount of time, which I wasn't expecting. I thought this would take a lot longer, but alright, that's enough for today.